They've got me backed up right against this thing here. Okay, we'll go from current slide. Had no new people come in. Okay. As far as announcements go, I don't know of too many that are of great importance that I think would be of interest to you. If any of you were thinking of applying for the NASA's Community College Aerospace Scholars Program, which I sort of doubt, but in case you were, the deadline is today. You have to get your application in today. Tomorrow, if any of you are interested, it is the Miss Lawson State coronation will be tomorrow evening at 7 o'clock at the Bessemer Civic Center. That's just next to the Bessemer campus there at 7 o'clock. And I won't be able to go because I've got a class that meets until 7:45, so I will not be there for sure, but it should be quite nice. Trying to think if there are any other major announcements. I know the volleyball team has a tournament this weekend at Friday and Saturday at Gadsden State Community College in Gadsden, so the times have not been released yet, but if you happen to be driving by Gadsden Friday or Saturday, go by Gadsden State and cheer the team on to victory. Don't know of many others. Any questions on anything we've covered so far? All right, now, let's just do a quick review here, because some of you I know have been out for a little bit. We have finished chapter 5. I've given you the test, and I don't know if everybody's turned it back in. I don't think so. I think I'm still missing, wait a minute, I think they have. So I think I may have returned those tests to you. If I have yours, let me get them to you. I think I've returned them all. Okay. The second test was on chapter 8, and I'm still missing 1, 2, 3, 4 tests for chapter 5, maybe. 1, 2, 3, 4. Huh? Second test, right. Okay. So be sure you get those in when you can. The third test was on matter. Okay, and you don't have the third one. Okay. Second or the third. Okay. That was chapter 12, matter.
Oh yeah, I don't have a second one.
Okay. Okay. Test 2, you don't have that?
I have 2. I did 2. I need 3.
Okay, you have that.
I did that.
You get you don't have that?
No, sir. I don't have 2 or 3.
Okay. So that's that one. Okay, here's test 3.
Thank you.
Thank you, sir.
Now on that one, you'll notice there are 2 corrections.
This test 2.
Yeah. On number 3, I've never seen anyone write 50, 00. I thought, what in the world do they mean? Do they mean 5,000 or 50,000? So I had to work the problem through backwards to see what they meant, and they mean 50,000. So that 0 up there by the pound, between the last 0 and the pound, that means 50,000. And then, of course, on the B part, what would be the compression? What would the compression be if the weight were 60,000? So there's another 0 in there. I can't believe that no one has caught that on their test bank. It's incredible.
So what is test 2 on?
Test 2 is from chapter 8, I believe it was, and test 3 from chapter 12. Okay. Any other questions? All right. We're now in chapter 16. got me so, I guess cleaning people or something have just moved everything forward as I'm pinned against the board here. Okay, so let's get back. We are talking in chapter 16 about wave motion and sound, and we are in section 16.1 still, okay? We almost through with 16.1, we'll be moving to 16.2. We're just at the point of talking about interference of waves from two sources. In fact, two topics here, interference and diffraction. So if there are no questions, let's start with interference. And I was going to write on that, but there's just not enough room to write, so let me go here and pick up my pen. Okay. So, remember when we were talking about waves in general, okay? Now, the easiest illustration of this is transverse waves, but it also works with longitudinal waves. But if you have a transverse wave that does something like this, okay, and then you have another wave that's doing something like this, obviously a lot of them are going to cancel each other out, okay? That is called interference. When a trough, okay, here is, I've covered my work here. All right. Is it Emily? Yeah, okay, I thought so. All right. And we just went over if anyone was missing any tests. Have you gotten test 1, 2, and 3? Huh?
I said I didn't get my test back.
Okay, I can't hear, sorry.
I said I didn't get my test two back.
Okay, I haven't given them back because not everybody's turned them in. I gave back test 1. I'm still missing tests from 4 people, test 2. But the question was, have you gotten test 3? Oh, you haven't. Okay. But you did turn in test 2. Right, okay. I thought you had, but okay. Work done. 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 Okay, there's test 3. Okay. So, we're in chapter 16 now. This is wave motion and sound. And we had talked about waves, and I just drew a couple of them showing a lot of interference there. And what interference is, if a trough, okay, the trough is the lowest part. If a trough crosses a crest, this is the crest for the second wave. If they superimpose on each other, they basically almost cancel each other out, okay? The water level is nearly undisturbed. This is in a tank of water. Okay. Okay. And that's an example of wave interference. That's pretty ugly writing. Wave interference. Okay? Now, we'll talk about diffraction in just a minute. Here was the illustration of that. All right, everybody got this? That's what I had up earlier, but there wasn't room to write the verbiage. So go back to the correct slide. All right. Now, you can't get in and out here very easily. Okay, here is an actual picture of a wave generator with two waves being generated here. Now, I'm just going to make an assumption here that the blue part here is the crest of the waves and the black part here is the trough of the waves. It may be reverse of that, but it doesn't matter. That's what it is. So this one is emitting a crest to trough, a crest to trough. The wave is doing like this. This one's doing a crest to trough, a crest to trough, just like that again. Now, when they combine with each other, what you see happening here, see these they call these wave fronts. When they superimpose on each other, you get a sort of a super crest, okay? And what you can really see easier on this is kind of the super trough where they cancel each other out. And you can see right here's a line, right there's a line, right there's a line, right there's a line, where they almost are canceling each other out. There is no crest or trough. Even though you see the work coming in, this is where basically they're canceling each other out. That's wave interference, okay? There's superposition where they're getting stronger, interference where they're wiping out. And this is, they call those places where they cancel each other out, nodes. Here's a representation. See, now what you got here, the way they've drawn this, let's say these are the crest, the brown crest and the green crest, okay? Now, they're showing these, where they crest on top of each other, they're showing that as a node. I don't think that's quite true. It's right where they're completely anti each other, and that would be not quite on this way. This would be places where you have the maximum crest, where they are reinforcing each other. Let me see if I can get a good picture of that. That would be right here, and you see that's not a node. That's where they're reinforcing each other. The nodes are where they're canceling each other. Nodes meaning nothing. You know, you got zero motion there. They just drew their lines in the wrong place, but what they're showing here are the maximum amplitudes there and there and there, okay, and here and here. That's where they're max. That's where the peaks are the greatest, where the two of them coalesce. The nodes are where in between that, where they cancel each other out, okay, and that's those. And you can almost see this would be the trough of the crest of this one, but it's the trough of this one, okay? So that would be your node. The crest of this one is right where the trough of that one would be. Crest of this one right where the trough of that one would be. So they're alternating and making almost no motion right here, okay? That would be, that's where your nodes are. That's what you see here. They drew the lines in slightly the wrong place here. Okay. Now, this is water waves. You might say, does this apply to sound waves? Because y'all are going to be interested in sound waves. Well, yes, it will, because sound waves will also cancel each other out or reinforce each other. And that basically is part of what gives you the images in your sonography. Okay? Now, the next topic they have here is that of diffraction. Now, they did another illustration here they don't have, and this is try this activity. if you have two guys here, or a guy and a gal, you can't tell what it is, you know, and they're moving a cord back and forth, and they do it in sync, then they're probably going to reinforce each other, but they either positively or negatively. But if they do it counter to each other, then they could have a lot of dead time, like right there in between. This one's moving this way, that one's moving that way, but they're canceling each other out in the middle, okay? So that's another way of picturing interfering waves. Sometimes they're doubling, sometimes they're canceling, okay? So let's move on to diffraction. Diffraction, let me get my pen back. Every time I change slides, it has to disappear. Diffraction, this thing right here, is the property of a wave that describes its ability, this is a wordy one, to bend around obstacles. In their path. That's what diffraction is. And just about everything is the bending. Bending of waves, bending of light, bending of whatever you're talking about. That's what diffraction is. Now, let me give you a hint on how this is. These are waves coming in, okay? Waves coming in from a source far, far away, so the wavefront, that's the crest, we'll call them here, are all just about parallel to each other. You can picture this at the seashore. If you have a nice straight level beach, all the waves seem to be coming in parallel to each other. It's reasonable. But if you have a couple jetties there, what happens, this wave, when it hits here, it just keeps coming in the middle. But over here, it has to stop. So when it stops and this stops, the friction of the waves bends. This keeps coming, but the wave bends here, and that's the diffraction, the bending of the waves. Now they're going in all directions here. The energy is dissipated in a variety of ways. Here it's all coming in a straight line. And waves do that. In fact, I think the next slide, this is almost impossible to get in and out of this desk here, okay? If you got your text, it's on the next page. You'll see, now this again I think is a drawing. I don't think this is an actual thing, but this is what's happening. The waves are coming in. You have a jetty here that looks like these are made out of rock or something. And waves coming in, they keep coming about the same speed in the middle, but they slowed up around the edges, so the middle gets ahead and the edges are slower, and what comes out is a diffracted wave. Okay? And that's what we mean by wave diffraction. Does that happen in sonography? I'm pretty sure it does. Something gets in the way of the sound wave going, perhaps bone tissue or something like that. That slows it down and it bends around. That's part of what gives you the image that you're looking at. Okay? Now, the previous slide was also on this page, page 432, and this one is on 432 as well. There's a physics connection given on wave pools, and let's see if they have a picture of that. Yeah, this would be like that, a human-made wave pool that creates the waves, okay? And what is the place up near Huntsville or Decatur or somewhere up there? Point Mallard, is that it, that has the wave pools? Yeah, my mother-in-law takes grandkids there a lot, you know. back when they were younger. Now she'll be taking great-grandkids. They don't have any. But anyway, that's a fun place to be. And I assume over here at Splash Adventure, they have one there too. Is that right? Okay. So these are really popular in the summertime. This time of year, lacking in popularity. Okay. And I didn't quite get her before she left. I think that's Tiara, but I'm not sure. Do you know? Huh? That's Sierra. Okay, I thought it was. I just caught a glimpse of her when she came in. But I thought it was her. Trying to find her again. I found her the first time. There we go. I can't get the pen to right. Okay, good deal. All right, so again, this is just the principle. They create the waves and there's not enough. And basically, that's what your machines will be doing that create the sonogram that creates the sound waves that goes in, and those are moved along, and you study the refraction, the bending of those waves. That's basically what you're looking at. All right. Oh, and here's kids playing in it. Okay. And this picture is also in the book. This is Typhoon Lagoon in Disney World. Okay. And looks like some pretty good waves being formed there. All right, now we're moving into 16.2 electromagnetic waves. Now, maybe y'all think you might not have as much to do with these, but basically, the sound waves that are being emitted, they're being translated into electromagnetic waves. So, you really will be dealing with these. That's what forms the pictures, okay? So, let me first give you some of the definitions you'll need. All right. What is an electromagnetic wave? Let me get my pen back. Okay. Electromagnetic waves. Okay. Now, if you can't tell by the name, it is dealing with electricity and magnetism. We're going to be talking about both of these in later chapters. And when we talk about them, we'll talk about electric fields and magnetic fields. And basically what an electromagnetic wave is the promulgation of energy from those fields. So it's sort of bizarre they have this before we actually talk about the fields. But electromagnetic wave is a transverse wave my writing stinks, okay, resulting from periodic disturbance in an electromagnetic field. I can't spell. Okay. That has both an electric component and a magnetic component. They're each perpendicular to each other, and they're each perpendicular to the wavefront, the direction of promulgation of the energy. Okay? Now, is any matter being moved in an electromagnetic wave? A water wave? Yeah, matter is moving. Water is moving. Sound wave? Yeah, air is moving. Okay? My transverse wave of a hose across the ground. Yeah, the hose is moving. Is any matter moving in an electromagnetic wave? No. It's the field energy that is pulsing. That's what creates. So how can we call it a transverse wave as opposed to a longitudinal wave? I mean, there's no matter moving. Well, that's because, as it just said, your electric field is going like this. Your magnetic field is going like this, perpendicular to each other and perpendicular to the promulgation of the wave energy, the wave front moving like that. Now, why is it important that there is no matter moving? Electromagnetic waves can go through space. They don't need matter to do. In fact, they travel best in a vacuum, basically space. They will travel through air, they will travel through water, they'll travel through solids, they'll travel through all sorts of things, but they travel best in a vacuum where no matter gets in their way. Okay? So that's what an electromagnetic wave is. Now, if you remember back, in the last section, early in the last section, we talked about the wave velocity is equal to the wavelength, lambda, times the frequency, f, where lambda is a length measurement, like centimeters, meters, miles, inches, whatever. Frequency is per second, cycles per second. So basically, a cycle is not a unit, but a per second is. So now you have centimeters per second. That's a velocity. Now that would be for sound waves or any kind of waves. Okay? Electromagnetic waves, something really special here. They always travel at the speed of light. That is a constant of nature, c. So c is equal to lambda f. This is your wave velocity of an electromagnetic wave, the speed of light. Okay? Now that speed of light, they're going to give it to you in SI units, is 3.00 times 10 to the 8th meters per second. Now 10 to the 8th, okay, let's get this. A meter, remember, is about, excuse me, sorry. If you notice the doorknob there on the door, that's about a meter off the floor, about the distance from your opposite ear to the tip of a finger, you know, when you're stretched out like that. That's a meter. Well, this is 3 times 10 to the 8th. Now, 10 to the 3rd would be 3,000 meters. 10 to the 6th would be 3 million meters. 10 to the 8th is 300 million meters per second. That's pretty fast. That would be 300,000 kilometers per second. Now, just to picture how fast this is, if you had a light beam on the equator, pick a place on the equator, Quito, Ecuador, that would be a good place. That's someplace right on the equator. Sorry. Just need to loosen things up. Okay. And so let's say right on the equator, you were able to emit a light beam. Now this is going to be tricky because you really can't do this, but you made the light beam so it traveled around the equator. Okay? Around the equator. The whole Earth. Okay? It could go more than 4 times around the Earth in 1 second. That's how fast light is. 300,000 kilometers per second. Okay? It's fast. Where lambda then is wavelength. You can catch from that length. That's a length measurement, centimeters, meters, millimeters, inches, feet, yards, miles, whatever. Frequency is per second. 1 over second. You sometimes refer to it second to the -1. Sometimes people use this, CPS, cycles per second. Cycle is not really a unit, it's just saying how many wavelengths does it do in a single second. That's its frequency. Okay? Now, since this is a constant of nature, then we can say that, let's pick one, either one, lambda is equal to the constant speed of light over frequency. Or frequency is equal to speed of light over the wavelength. What this is saying is these are inversely proportional to each other. The higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength. Okay? So, and they relate by this formula. Okay? So as frequency increases, the wavelength shortens, and vice versa. So let's do example 1, page 434. Does anyone need this any longer? Okay. The FM band of a radio is centered around the frequency of 100 megahertz. So that is a frequency of 100, and this second zero is significant here, megahertz, MHz. Now, does anyone know what mega means? Kilo is 10 to the third, mega is 10 to the sixth. Okay? So this would be written in scientific notation, 100 times 10 to the sixth hertz. Well, what's a hertz? A hertz is a per second. S to the minus 1, or 1 over S, however you want to phrase that. Okay? Now, if you don't like having 100 there, you could move the decimal 2 more places, and what the book does is make it 1.00. Now you don't need the bar over it because all three of those are significant, times 10 to the 8th, because you just made this number smaller, so you make that number larger. And that would be per seconds, or 1 over second, a hertz. Okay? It says find the length of an FM antenna if each arm must be a quarter of a wavelength. Each arm must be the quarter of a wavelength. So find the length of that antenna. Okay? What you have to find first is what's the wavelength. Do they give you enough information to get the wavelength? What's the formula that relates frequency, wavelength of electromagnetic waves? Just had it on the board. Frequency is equal to what? A little louder, I can't hear. Lambda? A little louder. Okay, yeah. Lambda F is equal to C, the speed of light. Okay? So yes, we do know, because we know the speed of light. It's a constant. Now, if you don't remember that or know it exactly, I'm pretty sure your book has somewhere a table of your constants. Let me see if I can find it. Every book puts it in. Here we go. Common physical data. Back inside cover of your book. Speed of light, number 5 down the list. The symbol C, which we have here, and it's 3.00 times 10 to the 8th meters per second. Exactly what we used before. So we're going to do that. Now, since we're looking for the wavelength, do you want to solve this for wavelength first, or do you want to plug the numbers in and then solve? I don't really care too much. You tell me. Second? Plug first? Okay, so this will be lambda. We don't know. That's what we're looking for. Frequency of 1.00 times 10 to the 8th per second, or 1 over second, is equal to 3.00 times 10 to the 8th meters per second. That was what was just in the back of the book, and we just had it on the slide. So what we're going to do to solve for lambda, we're going to divide by 1.00 times 10 to the 8th per seconds. I may just write that as over second, 1 over second. Divide this by 1.00 times 10 to the 8th per second. The per seconds go out, which are nice. The 1 will go in the 3 exactly 3.00 times, and 10 to the 8ths go out exactly. So this will be meter. That's the units that's left. That will be your wavelength. And it said here the length of the antenna if each arm must be a quarter of a wavelength. Now wait a minute. Yeah. A quarter of a wavelength. Well, if a wavelength is 3 meters, what's a quarter of 3 meters? Three over 4 meters, right? Well, each arm would then have to be 3/4 of a meter, which would be 0.750 meters. You write that with 3 significant digits. This 0 is not significant. Zeros in front of a decimal number, a decimal, are not significant unless there's some number in front of them. But just by themselves, they're not significant. So you need that third 0 there, that 0 at the end. That would be how long the arm of that antenna would have to be. Now, 3/4 of a meter is not that long. If a meter is about like this, 3/4 of a meter would be something like this. So about an arm length. And FM antennas don't have to be all that big. Now the AMs, they have to be quite tall, okay? But the FM don't have to be that big. So 3/4 of a meter. Now, let's go back. Any questions on that before I delete it? Before I shift to the next? So let's go to the next, back to where we were, going back and forth here. All right. Go from current slide here, and I need my pen back. Where it is. There we go. All right. The electromagnetic spectrum, definition for that is the entire range of electromagnetic waves. I'm just going to call them EM waves, electromagnetic waves. Okay, classified according to frequency. That's 2 C's, sorry. Frequency. Okay. Now, here is an illustration of that frequency period. Okay? Now, remember, speed of light is really fast, so your frequency is usually going to be fairly high. This ranges from 10,000, that's 10 to the 4th, up to, goodness gracious, 10 to the 19th, which is an enormous number. That's a 1, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0. Huge number. 6 sets of 3 zeros following a 10. It's a huge number, okay? Now, just a little hint. The higher the frequency, the higher the energy. So, energy's down here, you're not even going to notice. They're not going to bother you at all. But because these are the shortest wavelength, lowest frequency, these are your longest wavelength. Okay, if you were down here, if your antenna needed to be 3/4 of a wavelength, this is 3/8 7,000 meters. Okay, so then you're 750. Yeah, 750 meters long. That's about 8 football fields in the end. That's going to be a huge antenna. Okay, so this is what we call radio waves. Low energy, long wavelength, low frequency waves. This is what they call the broadcast band. Now, I don't know if any of you remember, you probably don't, you're too young. CB's, Citizen Band, you don't. What did they call it? There was some way you signed on to that. I don't even remember it, but they wrote songs about it. It was a big deal several decades ago. Now no one uses them. Well, have you heard of ham radio operators? Probably not that either. There are people that operate radios and talk all over the world. It's really a pretty good hobby for those who, it's not too expensive either. One time it was more. These are what we call short waves, even though these are even shorter. And then you get the TV bands here. Now, they left off where these are broadcast bands. 10 to the 6th, okay, need to get down here. 10 to the 6th is megahertz, because these are in hertz, cycles, frequency in cycles per second. That's megahertz. This is your FM band, and your AM band is down here. These are in kilohertz, but it's hundreds of kilohertz, so that would be down here. So AM is here, FM is here, TV is up here. They're also in megahertz, but usually at a little bit higher frequency. Okay? Now, microwaves are here, even higher frequency. Now, you would think with microwaves that means shorter waves, but they're not. These are long, well, yeah, they're shorter than TV and broadcast, but they're not nearly as short as these up here. So these are your microwaves. And y'all know anything that uses microwaves? Certainly a microwave oven does to cook food. But you see all these cell towers around? They're usually microwave boosters. Most of your traffic, your cell, the signals you get there are microwaves, okay? Because they come through those cell towers. Now you get up here, and this band up here, this is pretty high frequency, shorter wavelength. This is infrared, which is basically heat energy, generally heat energy. And this is all what we call visible light. This is basically just about all that gets through our atmosphere. Thank you very much. Some of this comes through too, for sure, but this is what mostly comes through visible light. And what's on the lower frequency end, the longer wavelength? Red, orange, yellow, green, blue, indigo, and violet. Y'all remember Roy G. Biv? You have ever heard of that? That's how I remember. Most people remember that. Then beyond this is ultraviolet rays. These are higher energy, higher frequency, and this is where we start getting problems. Ultraviolet rays damage tissue. Okay? Skin cancers caused by ultraviolet rays. Cataracts in your eyes caused by ultraviolet rays. Ultraviolet rays. Actually, the wrinkling of skin. Some of these do come through our atmosphere, and when they do, they cause problems. Now, these folks that I call them the sun worshipers, the S-U-N, sun worshipers, they get out there and lay in the sun all they can to get as dark as they can. Wait a few years, a few decades, and they'll be as wrinkly as you can imagine. Okay, they'll look like prunes because you're damaging the tissue. What is it that creates the suntan? Your body is trying to send, isn't it, melatonin? yeah, to the surface and trying to help block those ultraviolet rays from damaging tissue. And those of us who are lighter complected have less melatonin, and we are more susceptible to skin cancers. I've had one removed here many years ago. This is precancerous here. I put sunblock on it every day, fall, winter, spring, summer, every day. I have to put sunblock on to keep that from advancing to skin cancer. Okay? Ultraviolet rays cause that. I've already had both cataracts removed. My right eye about a decade ago, left eye this past summer. Okay? From ultraviolet radiation. It destroys, it damages tissue. Now, some of you are a lot more fortunate. You have more melatonin in your skin, so you don't have to worry as much as we do, but you can still get it, okay? So it is an advantage. Oh, beyond that is x-rays. They're not harmful, are they? Yes, they are. If you've ever watched, have you ever had x-rays taken? Where? Hospital? How about dental office? Huh?
Just had one Monday.
I'm sorry.
I just had one Monday.
Oh, you did? Okay. And did that technician stay out there with you when the machine was on?
No, they wouldn't have it.
Oh, went behind the wall, didn't he? And looking through a glass. And did you notice that glass? It was dark. Why? Lead in that glass. That wall, believe it or not, had lead in it. If you looked at it from the side, that was a thick wall, thick glass. They have to stay out of there because you didn't get enough to do any harm to you. You just got enough to take measurements. They're in that room every day. They have to keep out of excess x-rays. If you had noticed somewhere they're wearing a little badge or a pin or something, that had a detector on it. And if they got too much radiation in a given month, they can't go to work the next month. Okay? Not good. Okay? That's no paycheck. Okay? So x-rays are harmful. I remember back, y'all wouldn't remember this, but there was a shoe company, I think it was Keds. I think they still make Keds, I don't know for sure. And yeah, and I believe it was them. And they had their own shoe store at one time, and they advertised, come in and we'll fit your shoes and we'll take x-rays to see if your foot fits well or if it's crushing your bones together. Well, they said, hey, you can't do that. I mean, your people in the store and these kids don't need to have lots of x-rays of their feet. Cut that out, and they did. Had to. And up here are the very most deadly rays. These are the gamma rays. And these, like I said, are deadly. They don't kill you on the spot. They damage tissue so severely that you get incredibly sick and die a slow, miserable death. Okay, I hate to put it so mildly, but that's exactly what happens. Okay, you don't mess around with gamma rays. Okay. Fortunately, our atmosphere blocks out just about all of these, just about all of those, most of these, but it doesn't get them all. Some gets through and only allows this through. Those can come through if they want to, it's fine. Okay? But something you may have been hearing about lately, remember what I said infrared waves were? Heat. Well, here's something else our atmosphere does. And you may have noted this, probably not today very much, but last summer, yes. And even in the wintertime, you'll notice it. On these bright, sunshiny days, if you leave your car out in the parking lot, not under a tree, but out there in the sun, and have the windows all closed, you go out there to get in the car, is it warmer or cooler than the outside? Hot. Really hot. And remember, every summer they have these programs go out and things about not leaving children or pets in a car in a parking lot. They can die. And why? heat because our atmosphere allows these rays in. These don't come in because they're too high a frequency, and there's a portion of the atmosphere way up there called the ionosphere. It blocks most of these. But our entire atmosphere traps these. The heat rays, they don't have enough energy to get back out. Okay? Just like the light comes into your car, but coming through the glass, it uses a little bit of the energy to get through the glass. So now, because the speed's the same, the wavelength, the frequency decreases because the energy is decreasing. Your wavelength increases, and now it can't make its way back out through the glass. That's why your car gets hot inside. And that's why our planet gets hot when too much carbon dioxide, methane, and other things like that are in our atmosphere. They keep more of the heat in, and we call that the greenhouse effect. It's exactly what a greenhouse does for people raising plants. The light comes in, heats it up, and it can't escape, so the greenhouse gets warm. They can grow plants or keep plants alive all winter. We have a little greenhouse in our backyard where we put some of our ferns and other outside plants that we can't fit in the garage, okay? We put them in there, and we will supplement that on the very coldest day with little heaters. Actually, what we do, we put the old style Christmas lights, the ones that got really hot and dried out your tree and they don't like you to use anymore. We gathered those from all my in-laws and outlaws and everybody else who had any they were going to throw away, and we strung them around in our greenhouse, and they produce a lot of heat. So on a very cold night, we plug in, and our greenhouse looks very festive, but it's also keeping the plants warm. When it's not going below freezing, we don't bother turning it on. But on an extraordinarily cold night, we actually put a little heater out there and try to keep the plants alive there. But most of the time, that trapped infrared heat radiation stays inside the greenhouse. Okay. So that's your electromagnetic spectrum, from very low energy, low frequency waves all the way up to high frequency, high energy rays. These, of course, are your short waves that they penetrate like crazy, and these are the longer waves, okay, like the radio waves. Now, I don't know, no one listens to AM radio anymore, do you? Okay. Back when I was a boy child, FM was not very popular, and people listened to AM. The incredible thing about AM, because it's long wavelength, these wavelengths will bend in the Earth's atmosphere, sort of like the bending, the diffraction of waves that we talked about before. Because they were low energy, they would bend, and you could, on a good night, pick up Fort Wayne, Indiana, Chicago, New York on an AM dial, okay? You could pick up stations like that. Of course, there weren't as many stations as we have these days. The FMs are basically line of sight because those are larger frequency, shorter wavelength. They don't bend in the atmosphere, so they're basically line of sight. So basically, if you're not within sight of a radio antenna, now you may not be able to see it, but you probably are not going to pick up. That's why when we drive from here to Atlanta, somewhere about on the other side of Oxford and Anniston, we start losing our FM stations. So we have to dial and get on an Atlanta station and then carry that the rest of the way until we get outside of Atlanta, and then we're going to Augusta. We pick up the Augusta FM station. They just won't. You can't do them much past the line of sight. A little bit past, but not too much. And that's why they have cell towers for the microwaves, because they only do pretty much line of sight, so they send to the next tower, to the next tower, to the next tower. Have you ever? Yeah.
So how does Sirius play into that?
Others what?
So how does Sirius play into that?
TV? Is that?
Sirius. You ever heard of Sirius radio?
Oh, Sirius. Okay. Okay, good. Good question. Sirius radio, satellite radio. So the satellites are up there fixed over us. Okay, I don't think we'll cover that in this course, so I'm glad you asked. Same type of thing that does your GPS for you. They have satellites that stay over the same place in the Earth. As the Earth spins, they stay right on top. So Sirius is up there, they can hit the entire hemisphere that they're over. Okay, so that's how Sirius works. That's how GPS works. Because they're up there and they hit the whole globe. Half the globe. They don't hit the half on the other side. They hit the whole hemisphere that's toward them. So that's, you don't ever lose Sirius, do you? Okay, it's pretty serious. No, I didn't say that. Okay. I did say that. Okay. Hey. Okay. Hold on, let me turn off my recorder. All right, good deal. Any other questions on the electromagnetic spectrum? All right. There is a blurb here in your text on evading radar, which is, guess what? Electromagnetic radiation, okay? And there's a picture here of the stealth aircraft. And you see, when you look at it head on, it's almost invisible. You don't even see the wings out there. They are very small, and it's made out of material that does not reflect radio waves well. So that's how they avoid most of radar. But anyway, that finishes 16.2, and you can do any of the odd number exercises that are in the back of the book, answers in the back, 1 through 17. Yeah, that's it, 1 through 17. Okay. Now, perhaps what's of more interest to you would be this. Okay, we're not quite ready for that slide yet, so let me get out of that and go back to this one. Okay. All right. We're now 16.3, maybe the heart of what you need in this course. So you need a lot of electricity and magnetism too, sound waves. Okay? So let's start with what in the world sound waves are. We've talked about them already. I've brought them up and used them as examples several times. But sound refers to those waves transmitted through a medium with frequencies capable of being detected by the human ear. Okay, I don't like this definition. And it's produced by a vibrating source. I don't like the wording either. Okay, because actually what y'all will be dealing with is they're like sound waves, but not quite, because they can't be detected by the human ear. They're ultrasonic. That's what ultrasound means. Ultrasonic waves, higher frequency than you would detect with your ear. Now, are there sound waves that you can't hear? Sure. Anyone ever hear of a dog whistle? You've never heard a dog whistle. My dog doesn't whistle. No, I'm just kidding. But dogs can hear it because they have different frequencies they can hear. So that's why they said human ear here. But yes.
I thought some people can hear it, but some people couldn't.
Right.
But my stepdad can't, but my mom does. And I'm learning how to make that noise, and it's driving my mom crazy.
Yeah.
But my stepdad can't hear it.
Right. And you just hit on something. When people age, their olfactory abilities decline. Okay? We don't hear as high a frequency. And this actually happened over in, I believe it was England. Back when cell phones were brand new, and kids were just getting them. They were not new enough that kids couldn't afford them, but they were getting them. And they had these variety of ringtones. And they found out that they could set the ringtones at high enough frequency that their teachers couldn't hear it, but they could. And they could be doing all sorts of bad stuff in the classroom, mostly texting. They wouldn't be talking, of course, but they would have the ringtones. Until, of course, they happened to hit a young teacher who had exceptionally good hearing, and she realized what was going on, and they put an end to all of that. And that's why sometimes in especially lower grades of school, they prohibit phones in the classroom because students could set them up so they could be beyond what adults could hear. And that's probably what's happened, is you have very good hearing, whereas your stepdad probably is more like me. Okay. My father-in-law speaks at a frequency that I can, especially over the phone, I can't tell who I'm talking with. I can make out most of what he says, but usually you can tell when you pick up the phone who it is. But his frequency is one of those that I'm really bad at, and so if someone's like talking and sound like they know who I am, I just guess it's Mr. Brazil. Because his frequency just happens over the phone. In person, it's not as bad, but over the phone, it just is off enough that I cannot tell who it is until I figure out, well, he seems to know me, it must be Mr. Brazil. Okay. So, we tend to lose that. And I've noticed that, let's see, which is it? My right ear, I think, is far worse than my left ear, though they're both bad, because if I'm facing my alarm clock with this ear on the pillow, I don't hear it. The alarm clock, and I'm right there, it's right there at me. If I'm laying with this ear exposed, I always hear it. So you would think facing it, I would be more likely to hear with this ear. That frequency that's on that alarm, I don't hear it in this ear. I hear out of both ears okay, but this frequency is different. Yeah. So, that does happen. And it happens worse as you get older. I need a hearing aid. I don't know, just never gotten it yet. The trouble is, and y'all may realize this later on, glasses, just about everything is covered by insurance, but not hearing aid. It is not. So you have to pay sometimes pretty big bucks for that. And that doesn't make any sense to me. You would think that would. And part of my hearing loss came from when I was in the Navy. I was on an aircraft carrier, and the launching and catching of aircraft was right by where I slept at night. And because I have big ear canals, the ear sound suppressors would fall out of my earplugs would fall out of my ears. They didn't have the spongy ones like they do today, and so I had hearing loss. And I thought for sure the VA would help cover it. And one of my students worked at the VA and said, yes, they will. She got hers there. Well, I went there. I called to get in touch with them. Nope, you make too much money. We don't cover it. So, that's a pet peeve of mine. I'll get off of that now. All right, there's what sound is. Now, how about the speed of sound? Think it's as fast as light? Any ideas? Would sound travel as fast as light does? Nowhere close. And you can tell this basically. Have you ever seen lightning strike? Do you ever hear thunder at the same time? Most of the time, not. If the lightning is really close, yes, it thunders right then. You better watch it because that was a close hit. But most of the time, we'll see the lightning long before we hear the thunder. Or if someone is shooting something that you can see a flare, you'll see the flare long before you hear the pop. Okay? Fireworks. You'll quite often see the burst in the sky before you hear the boom. And that's fairly close, okay? But the speed of sound is considerably shorter than the speed of light. Speed of light, remember, was 3.00 times 10 to the 8th meters per second. The speed of sound in dry air at 1 atmosphere of pressure, 0 degrees Celsius, which is freezing point, is 331 meters per second. That's a difference of a factor of close to 1,000,000. Light travels close to 1,000,000 times faster than sound does. Okay? Now, when you just heard me say that, the speed of sound in dry air, we don't have much dry air around here. It's usually got a lot of moisture in it. So our sound will probably do a little bit faster than this. 1 atmosphere of pressure, we're usually pretty close to 1 atmosphere of pressure. Go up high in a mountain, it's not going to be as much. If you mostly that would be where your atmosphere of pressure would change. 0 degrees Celsius, when we're warmer, which most of the time we are than that, the sound travels a little bit faster, the warmer the air is. So we'll be a little bit faster than that. But all those factors come into play. The most important of those, the changes in humidity and temperature cause a variation in the speed of sound, and it increases with temperature at a rate, and I'm going to give it to you here. So velocity, this will be the velocity of speed in sound. This is V, okay? Is equal to, no it isn't. I thought this was on the slide. It's not. 331, that's meters per second. Now this is SI units here. Plus, and here's what you do. 0.61, that's not a lot of difference. Meters per second per degree Celsius. Multiply that by your temperature in Celsius. And does anyone know what room temperature is in Celsius? Very close to 20 degrees. So say you're going from the freezing point of water, that would be basically what your freezer and your refrigerator would be, the freezer part, about 0 degrees Celsius, up to room temperature. Let's do that. Multiply by 20 degrees Celsius. Okay, degrees Celsius are going to go out, and 20 times 0.61 is 1.22. So that will go from 331 meters per second to 332 meters per second. Not a lot of change, okay? And the hottest day of summer won't get more than 40 degrees Celsius, so that only changes 1 more meter per second. So not a lot of change under normal temperature regimes. But what if you're talking about the speed of the speed of sound in U.S. units, U.S. customary, okay? That would then be V is equal to 1,087 feet per second, okay? Now remember, a meter is a little more than 3 feet. So if you multiply 331 by 3, you're going to come out something 993, which is pretty close to 1087. So that's where that number comes from. Plus 1.1 foot per second per degree Fahrenheit. Now, one reason this is a bigger number, two reasons. You got more feet per second for the same, meters per second, okay? That's a factor of 3. But then a Fahrenheit degree is not quite half of what a Celsius degree is. So a Fahrenheit degree is smaller foot per second. So this adds up. So you then, but here is the strange part. You have to take the degrees Fahrenheit, temperature in Fahrenheit, but first subtract 32 degrees Fahrenheit from it. Because water freezes at 32 degrees Fahrenheit, so to get it from the freezing point of water, you have to say the difference in your temperature. Like right now, it's probably 68 degrees. 68 minus 32 would be 36 degrees. So 36 times 1.1, that would be 3.636. That would be 39.6, almost 40. So let's just add 40 to that, and that would be 1127. That would be how much it increased. That's too much. Isn't it? Yeah, that's about right. So that would increase about that many degrees. I mean, that many feet per second. All right. Seems way too much, though. Okay. All right. Enough of that. Those are the two formulas you're going to need to use a bit to calculate changing velocity of sound in air. So let's do example 1. Find the speed of sound in dry air at 1 atmosphere of pressure if the temperature is 23 degrees Celsius. So we got T, and this is in Celsius, 23 degrees Celsius. And what's our formula there? V is equal to 331, that's meters per second, plus 0.61 meters per second per degree Celsius multiplied by 23 degrees Celsius. Okay? Pull out your handy-dandy calculators, punch away, see what you get. I must not have done the other one right. Yeah, I was off. It should have been 12. On that other one, I said it went up 1 degree. It should have been 12 degrees. I mean 12 meters per second. I knew that seemed way too low. Because what does this do? Anybody? Anybody got an answer?
4,643.9.
Whoa, 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 whoa.
Oh, they say plus. I'm just lying. Hold on.
That's way high. You use the other one. Use 331 plus, okay,
345.03.
330,
345.
okay, 345 meters per second. Yeah, we only have 3 significant digits. Actually, we only have 2, but we'll let you get away with 3 because they have this at 3. 345 meters per second. That's what the book got. They're not being as picky on significant digits in this as they did in the other. And here's really why. This multiplication is the only thing that uses 2. When you're adding, you use whatever you got. Okay? So 345 is correct. Now, this is using your previous material that we had. Example 2, what is the time required for the sound from the explosion to reach an observer 1,900 meters away Wow, 4 significant digits. For the conditions in example 1. Okay, so we've got the speed. How do we get time? How is speed, time, and distance related to each other? Anyone remember? Speed, time, and distance. Frankly, units are your friends. Look at this. Velocity is measured in meters per second, so that would be distance, meters, over time, seconds. Units can help you out, right? That is exactly the formula. Okay? But we're looking for time here. So you want to plug and chug, or you want to solve for time first and then plug? I don't care much. Which way you want to do it? Anybody? Plug it in first? I thought you were going to say that. So what you have is 345 meters per second is equal to a distance of 1,900 meters divided by t. That's what you're looking for. That's the unknown. So what you have to do, which you would have had to do in the other one too, is multiply both sides by t, because you want that in the numerator, okay? And then divide both sides by 345 meters per second, 345 meters per second. You're doing the same thing, okay? This wipes that out, so your time is now 1,900. Now notice here the meters go out, and 1 over second is the same as second. That's a good thing for time to be measured in. So 1,900 divided by 345. What do you get? 5.5 what? 07 seconds. Well, we only have 3 significant digits there, so let's limit ourselves to 3 here. 1, 2, 3, look to the right, that's greater than 5. We'll call it 5.51 seconds. Let's see what the book got. Look at that. 5.51 seconds. Now, that means the explosion could happen. You'll see the flash almost immediately. Now, what is 1,900 meters? That's pretty close to 2 miles. Not exactly, but pretty close. That's 1.9 kilometers, and it's not close to 2 miles, about 1.5 miles, I'd say. Okay, you see that explosion, and then about 5.5 seconds later, you'd hear the sound from that. That would give you time to do this, okay, because it's probably going to be a pretty loud sound. All right. Let me go to this next table that I know is on here. And oh, there it is. All right. Now, going to write down what they say before this table. Okay? Well, it didn't take. There we go. Sound propagates faster in a denser medium than such as water, than in air. Okay? A less dense medium. Such as air. Now, I don't know if you've noticed this before. Been in a swimming pool, got down below water, sounds very different down there. You can hear things you probably wouldn't hear above, okay? Because sound travels differently in a denser medium like water. You'll hear more things. Now, I don't know if you ever watched the old Cowboy and Indian or Bank Robbers and Cowboys, you know, good guys, bad guys, movies on television, the cowboy movies, okay? What the Indians were noted for doing, if they were trying to see when the train was coming, this was especially the bad guys. The bad guys would put their ear down on the track. If they could hear the train coming from a long way away, because the metal is a far denser medium than air is. You wouldn't even hear it in air, but in the metal, you could hear it miles and miles and miles away, so they could set up their ambush or whatever. That would happen there. The reason is, in steel, the speed of sound in meters per second, almost 6,000. And what was it for in air? 331. Okay, much faster in steel than in air. And it'll travel a far longer distance as well. Now, some of the things don't quite match up here. Aluminum is not as dense as brass and steel, but yet it transmits a little bit faster. So there are other things involved than just density, but the denser the material, usually the more. So water, what is that? About 10 times, better than 10 times faster in water. But how about in a vacuum? Doesn't go at all, because there's no molecules for the compression and rarefaction. Sound has to have that. It has to have moving molecules. The denser materials, the molecules are closer together, transmit much faster. Okay? The less dense material like air, very slow. 331, this is 0 degrees Celsius, 1094 feet per second. Okay? Water, much faster. Alcohol, not as dense as water, so a little bit slower. Don't be swimming in alcohol. Don't do it. Okay? It's not good. Okay, granite and all these are pretty rapid speeds. Actually, brass the lowest. That's rather strange, but it is. Okay, all those are basically within about the same range. So the denser the material, generally, the better more rapidly it transmits sound, but it's not all dependent on density. All right. Now there's several, let me just see what's next. Sorry, we have to go back and forth a few times here. Okay. Now, several features of sound, characteristics of sound. Let's do let me get my pen back. Goodness gracious, this is such a pain. Okay. First is intensity. Okay. What intensity is the energy transferred by sound per unit time through a unit area. Okay? So it's the energy transferred by sound per unit time per unit area. Now, energy per time, that's power. So therefore you can say this is power per area. And when you talk about intensity, that's measured in watts per square meter. That's typical units for sound intensity. Watts per sound per unit area. Watts per meter squared. We don't really use too much on the U.S. customary side because our unit of power is horsepower, and that's a huge unit. So we don't think of horsepower per unit per square foot. That would be rather strange. So we don't usually do it there. Now, another characteristic of sound is loudness. And you would think these would be related, and they are fairly close to each other. Loudness is the strength of the sensation of sound. It's a pretty nebulous sound. Of sensation of sound. Heard by an observer. Okay. That's fairly nebulous sounding definition there. Okay? And like I was saying before, the ear doesn't respond to all frequencies the same, especially if you start having hearing loss, but there is a huge range. There is a unit that we use to measure sound level, which is more like intensity, and that is a decibel. Okay? You get it, you call it dB. And I bet you, when y'all are doing your sonography, you're going to be doing a lot of measurements in dBs. Probably beyond the range that you'll hear because it's ultrasound, but a dB. Now, if you recall, D is a metric prefix meaning a tenth of, deci, a tenth of, and a bell, if you wrote this out, it's called a, let me see if I can find it, it's B-E-L. We call it decibel, but the B-E-L, they capitalize the B because it's named after Alexander Graham Bell, who did a lot of the early work in sound, developed the telephone, invented that telegraph, established Bell Telephone Company. We still use his name for that. So those are the two terms, intensity and loudness. So let's go back to the table that I was looking at before, but it didn't have enough room to write. And let's see that. Here are some of the ranges that we can hear. Some of you can hear. I can't. The threshold for hearing we count as 0 decibels. Okay, that doesn't sound like there's anything, but it's this is what we call as a log scale. What a log scale means is every power of 10, you go up 1 unit. So the energy involved going from 0 to 1 decibel is 10 times the energy of that sound. So a decibel is a log scale. And you'll notice here, as you go from intensity of 10 to the minus 12 to 10 to the minus 11, that's 1 power of 10. Well, actually, okay, they multiply it by 10. So it's 1 times 10. 1 times 10 again, that's this. The change here is 2, so 10 times 2 is 20. This is 1,000, that would be 3. 3 times 10 is 30. So this is how they measure that. They multiply the log scale by 10. Okay? So the threshold of hearing for you young people would be around 0 decibels. That would be 10 to the minus 12 watt watts per meter squared. That is scarcely audible. I'll never hear that, okay? Minimal sounds, decibel of around 10, yeah, you can hear that well. I'll probably not hear that one either. A ticking watch, it's been a long time since I heard a ticking watch. That's around 20 decibels. You can probably hear it, I probably can't, unless I hold it right up to my ear. Okay, that's about 30 decibels. Okay, that's very, very faint. But if you said the same thing, I would never hear it. I can see your mouth move, but I wouldn't hear it. That's because, this is true, what I hear from myself is what's transmitted through my bones. I don't hear coming in my ear, I hear this way, okay? So I can hear myself better than I can hear you, so, but I can't hear yours. Okay. Now, leaves rustling, refrigerator running. We got a pretty loud refrigerator. I can hear that. Leaves rustling, it's been a while since I've heard that. Average home, neighborhood, street noise, about 50 decibels. My wife will comment sometime, well, the dog's out there barking. I'll say, oh, she is? I can't hear it. That's normal neighborhood noise, okay? Normal conversation or a microwave oven. Frankly, our refrigerator is louder than our microwave, I think, but it may be close, okay? That's around 60 decibels. I can hear those, but they're pretty faint. It's like people whispering. I'm not quite close to it. Car, alarm clock, city traffic. Like I said, with one ear, the frequency of my alarm clock, I won't hear if it's right at it, yeah. But usually I can hear the 7, okay? And that gets pretty bad if you think about it. I may not hear a car coming when I start to walk across the street. I better look both ways because I probably won't hear what someone else would hear as a car comes. Garbage disposal, vacuum cleaner, I hear all those things. Outboard motor, noisy restaurants, yeah. So I'm sure I can hear in the 80s of decibels. Probably some in the 60s and 70s, but I'm definitely in the 80 range. Factory, electric shaver, screaming child, about 85 decibels, okay? Lawnmower, passing motorcycle, convertible ride on a freeway, around 90 decibels. Hair dryer, diesel truck, chainsaw, helicopter, subway train, about 100 decibels. Car horn, snow blowers, around 110. Now you're getting, okay, right, let me go back. Car, alarm clock, city traffic, that's what they consider loud. That's just what I'm beginning to hear well, okay? Garbage disposal, vacuum cleaner, they call very loud. That's normal for me, okay? That's not good. Car horn, snow blower, 110 decibels, they're calling that deafening. Unfortunately, I've heard too much of that. That's why I'm deaf, okay? Rock concert, prop plane, that's around 120 decibels. For a normal person, that could get to be painful. 100 feet from a jet engine, now that's not behind the jet engine, but feet from it on the side, or an air raid siren, 130 decibels, those can be really irritating. And a shotgun blast, don't get around those, okay? 140 decibels, you can do some damage to the ears, okay? So, that's your table of range of sound levels and intensities. Intensity, watts per square meter, sound levels, decibels. All right, I wish I still had the previous slide, but I don't, so I have to go back to it, and it's already deleted. Okay. Another characteristic of sound, and you'll hear people talk about this, and sometimes they use it wrongly, but here's what the pitch of sound. It's the effect of the frequency of sound, so it deals with the frequency of the sound waves on the ear. Now that's a really nebulous sounding definition too. We say higher pitch sounds have higher frequency than lower pitch sounds. So it's kind of depends on the person. And that's what makes it a little nebulous. But remember, I said what I'm hearing from my speech is mostly coming through my bone. Remember, they're denser than air. That's going to be the better transmitter. Okay? Does that mean I hear things the same way? I have a question for you. Have you ever listened to a tape recording of a conversation? You probably recognize everybody speaking except yourself. Have you ever noticed that? Okay, I don't know. I know we had a real good family friend when I was growing up, probably high school age or something like that. And one Christmas he bought our family a tape recorder. Now, it doesn't sound like much, but back then that was pretty new stuff. I mean, it wasn't new, but most people didn't go around buying tape recorders, but he did. And he didn't tell us he got it for us until he put it under the kitchen table, and my parents and he and his wife were sitting around talking and laughing and having a good time like they always did. And then he pulled it out and played it. And this got my dad's joke like crazy. He just cackled at this. My mother said, "Well, who's that talking all the time?" Because she recognized everybody else's voice but hers. Because we hear through this, we don't hear through that. And yet we hear everybody else. The tape recorder is picking up the sound waves. It's not picking up what goes through here. So when I hear myself, when I do play some of these back, I can't stand hearing it. It doesn't sound at all like I think I sound. But that's what I sound like, and it's pretty obnoxious. Sorry about that, folks. But I don't hear that. You hear it, I don't. But these people who are really good singers, what do they say they have? Perfect pitch. What they hear this way is what they're singing that way. Ask anyone who sat near me in church. I don't have perfect pitch. Nowhere close. But I don't know what it's sounding like because I don't hear it. Unless someone played a tape recorder and I'd burn it. But no. That's why. And we'll get to that a little bit later. Sound, the pitch of a sound is the effect of the frequency waves on your ear. If it's coming through the bones, it's one pitch. Coming through the air, it's a different pitch. But it's the effect that you have. Now, they talk a little bit about beats, but not too much. So I'm not going to get into that all that much. But let's go now to the... Sorry, just one thing on that slide, then we go back to this one. And you have probably had this in biology class or somewhere before, so I'm not going to go into gory detail about it. But here are the parts of the ear. And surprisingly, this probably isn't going to affect you much in sonography because you've got equipment that's measuring everything. But what we're measuring, and the whole purpose of this external ear, the auricle, all that kind of stuff, is to be an ear horn. It gathers the sound and moves it into the ear canal. I have a big ear canal because I think I've been pretty hard of hearing since a very young age. And so there's the ear canal. That's also considered part of the outer ear, external auditory canal. Okay? Now, here you see the bones and stuff. And this is what transmits the hearing from your voice because you get all this vibrations coming through here. It doesn't have to travel around and come in your ear. So that's why what you sound like sometimes is very different from what other people hear you sound like, or whatever. Now we're getting right at the edge here, the tympanic membrane. What's the common name for that? Tympanic? Eardrum. Tympanic drum, eardrum. That is the membrane there. That's what receives those vibrations and starts the process of vibrating ever so slightly. Now we're moving to the middle ear, okay? And these vibrations here move these little bones, the malleus, I think of that as a hammer, and the incus, that's the anvil type thing, and that is will bang on each other, so to speak, and that magnifies the sound. Now in here it says the stapes in an oval window. Okay, that I think is what they're calling the stapes and the oval window there. You have to get into the real nitty gritty of this to have this make a lot of sense. So I'm not going to go into it. And that leads to the round window here. There's a window, there's a window. This one they call the round window, that's the oval window. And anyway, it transmits the sound through here, the nerves, neural endings and stuff pick up. That gets you into the inner ear. And the inner ear, where it comes in, they call it the vestibule. Okay, well, it's like the vestibule of a church or something like that, where you come in. And then you start having these variety of things here. Here is the cochlear. It looks like a cochlear seashell, right? Okay. Have any of you had family members or stuff that had hearing loss, especially as young children? My wife studies hearing loss in young children. She's a researcher at UAB. She studies the cytomegalovirus that quite often causes hearing loss of young children. And a lot of those young kids, if they can detect them early enough, they can get cochlear implants that then enable the child to hear close to normal, even if they otherwise would have been almost totally deaf. But they usually try to put them in fairly early. So there's the cochlea, okay? Looks like a seashell. That's where it gets its name. And all in here you have these cranial nerves. Why they have Roman numeral 8, I don't know. But anyway, these nerves are what carry these signals that are picked up in all these canals and vestibules and cochlea and everywhere else, carry that sound to the brain. And it's just remarkable that we can hear. Remember that range we were talking about? Let's go back to that slide just for a moment. Look at the range of hearing. That's from intensity of 10 to the minus 12 watts per meter to 10 squared. That's 100 watts per meter. This is 0.0000000000000 or 001 watts per meter squared there, up to 100 here. That our hearing, your hearing anyway, can cover that big a range. That's incredible. That's ultimately incredible. Okay? And yet we can. Okay? And it's all done through here. The signal carriers, the nerves, electrical impulses carry these things to the brain at close to the speed of light. Not exactly, because it doesn't, but that's why people talk and we hear immediately. Well, they have to be fairly close to. So it's really an amazing system. Now, one thing that has very little to do with the hearing, well, it can. This is the eustachian tube. Does anyone know what that is? That's the tube that starts at the back of your throat somewhere and goes up behind the ear. Why would you have a tube there? Well, have you ever been on a plane flight or driving in the mountains and changing elevations fairly quickly? What happens to your ears? They pop. And the reason is the air inside your body is whatever the pressure you were to begin with, and then when you change elevation, the air pressure changes fairly quickly, and if you don't do something to equilibrate that, you could actually break your eardrum, burst your eardrum. And that's why sometimes people who have a sharp blow to the head, will sometimes lose hearing. In fact, Thomas Edison, I think, was working for a pharmacist or something like that, apothecary, something like that, when he was young. And he questioned something, and the guy got mad at him and popped him on the head with a flat hand right on the side of his head. He lost a lot of his hearing. Later, he said that was one of the best things that ever happened to him, because then he could focus on his work and not hear what anyone else in the factory or anywhere else was saying. He could focus, and it allowed him to do that. I don't recommend it, okay, but he said it came in good. So that's what this does. And what do they tell you to do if you can't clear it? Do that. You're blowing to increase the pressure inside to equilibrate with what's on the outside. Quite often when we have flown before and come down, that's when I have trouble clearing. So that's what people do. What they recommend is chew gum or something that keeps it moving, that helps you open that. Now, quite often kids, when they have a sinus infection or something like this, their tubes are really small because they're kids. They're really young. And if they get inflamed, then they shrink. And then, boy, those kids will do some screaming, because that's one way they found out they can make their ears get hurt. You know, that's why sometimes on those plane flights, those kids are screaming like crazy. You don't want to sit near them, but anywhere on the plane is close enough to them. But anyway, so there's the only other part there. All right. Now, the next topic we hit, we're not going to have time to do it justice, but let's at least introduce it here. It is the Doppler effect. And I bet you every one of you has experienced this before, whether you realize it or not. Okay? The Doppler effect. Okay. It refers to the variation, I can't write, of the frequency heard when a source of sound is either moving toward you or away from you. Let's just put it this way. Source of sound and the ear that you're hearing it with are moving relative to each other. Now, usually it has to be at a fairly reasonably high rate of speed. It doesn't have to be super fast, but that. Now, named after Christian Johann Doppler, I think he was Austria, physicist and mathematician, best known for his description of this. Now, basically what's happening here, remember, sound waves are pressure waves. Okay? That's things moving close together and farther apart. Now, if either the source of the sound or you are moving toward that, because the sound waves are taking up space, you basically hear them compress, which increases the frequency. If you're moving away or it's moving away, then the frequency sounds like it's going down. It's really the same frequency, but what you perceive is a change. And that's what we're getting at with, and now immediately I go out of this and back to this one, this. So, if this car is moving away from person B here toward person A, and their horn is on and they can't get it off, then person A is going to, it sounds like it's getting higher and higher frequency. Now, surely it's getting louder because the car is getting closer. and it's getting dimmer there. That's not what we're talking about. We're talking about the frequency, what sound. You see, the sound waves are getting further apart here, lower frequency. Closer together here, higher frequency. And that's why sometimes if you're at a train track and the train's coming down and blows on this whistle, the whistle sounds like it, of course it's getting louder, but it also goes up in frequency. And then when it's leaving, it goes down in frequency. The whistle's the same. It's just your perception of it on which side you are, whether the waves are further apart or closer together, higher frequency, lower frequency. This also, if police cars or ambulances or anything else is running a siren, when they're coming toward you, it sounds like they're increasing their frequency, going up in pitch, okay? Or when they're going away, it sounds like it's going down in pitch. No, they're the same, but your perception of it is that. That's the Doppler effect. Now, I don't watch that much television, but I just happened to catch an episode of The Big Bang Theory. This was several years ago, and it was around either Halloween or Valentine's, sometime when people dressed up in costume. And Shelton, that's his name, right? He went to the costume party in a T-shirt that was the Doppler effect. It showed, and everybody said, "Well, where's your costume?" "Oh, this is it. It's the Doppler effect." What? You know, that was settled with Shelton. I thought it was, of course, a physicist would find that funny than most. Okay, but anyway, that's where we'll leave off, I'm afraid, tonight, because we are running out of time. Where we'll pick up next time is the formula, the apparent Doppler shifted frequency. That's what we'll do next time. There weren't any homework exercises after 16.3. There will be after 16.4. And I think we'll finish chapter 16 next time, so there probably will be the test next time on chapter 16. There's my pencil. We'll pick up down here. And I need my eraser. All right, good deal, folks.